Okay, thanks. Thanks a lot for the introduction and for the invitation, and also the opportunity to run our challenge as part of CAMDA. So my talk will be kind of giving a background and motivation for this challenge in privacy preserving synthetic data that will then follow up with a more introduction and the results. And I guess to start with, it seems like an obvious question, but maybe this is something that it's worth thinking about a bit more. So why do we need privacy for doing machine learning with health data? And kind of to start with, there's of course, how could you not do an algorithm that's not private? It's not something that you could say. Obviously, it's a good buzzword for marketing, but then the question is, how do we really want to? How many people are really prepared to go beyond that? And of course, the technical reasons why we want to do this is avoiding leaking some of this sensitive data that we're using for our models from the results. As well as we heard in the morning, there was this other synthetic data challenge. So if we can create privacy-preserving synthetic data, we could share that more easily, and then that would make life a lot easier because you didn't have to use these secure processing environments like was also described in the morning. But the big question is, are we prepared to accept the loss in utility that comes from doing things in a privacy-preserving manner? Fortunately or unfortunately, depending on your point of view, our democratic decision makers have decided, at least for those in Europe, that privacy is something we want. So we already heard a brief mention of the European health data space. That was the regulation was approved recently, and it entered into force in March. And after a 4-year grace period, this will EU-wide provide a framework for accessing health data for research and development. The model is actually similar to what is already in use in some countries. And the basic framework is such that researchers can apply for access to pseudonymized data that they will analyze in a secure processing environment. But then there's I'm quoting this part of the regulation that very strictly says the results of the secondary use shall only contain anonymous data. And I've written the anonymous here in red to indicate kind of as a warning that this is, now we're talking about the anonymous as defined in the GDPR, which is kind of like really something that cannot be linked to an identifiable individual, not kind of some US-based definitions might be something more relaxed. Okay, so why is this a problem when we are talking about machine learning? You may have seen some of these pictures of how these machine learning models, and especially generative AI models, seem to be pretty good at memorizing their training data. With language models, at least the underlying models do memorize training data. In case it's kind of an instruction-tuned model, then it's a little bit harder to extract this. But if you're sharing the model, then it's easy to fine-tune it to undo this instruction tuning, and then you can kind of extract the data again. And also for image generation diffusion models, they also seem to be very good at memorizing specific training examples. So this is all very practical. What's maybe more interesting is that even classification models, under ideal conditions, they seem to be able to memorize specific examples, and that you can reconstruct these. This requires a lot of background knowledge, and this is not something that you could just do for a regular model someone has released. But it shows that these models do memorize examples that you can then reconstruct. Okay, so this is for the results. To debunk some kind of supposed privacy technologies. One, I guess, common solution for this is federated learning. So you just the data never leaves. So you kind of have an analysis where kind of there's a central coordinator that collects updates from clients. And the theory is that because the data never leaves, of course, that's private. Well, not quite. You're sharing these updates, and from these updates, it is possible to reconstruct the training data. This is results if kind of the adversary is kind of well-intended, just passively observing things. If you kind of now start being kind of having an active adversary, so someone who crafts a model to really extract the training data, it's possible to create models that give you kind of like perfect copies of the training data in federated learning. So this is obviously a problem then. I mean, if you have some data and then you're giving others access to that data through federated learning, how do you guarantee that they are not stealing your data? Synthetic data is another technique that has been suggested as a solution for privacy. Unfortunately, the problem is that if we are measuring the privacy using standard attack-based techniques that I will be talking about in a minute, it turns out that the standard synthetic data technologies without extra privacy protection. The same applies for federated learning. I mean, you can make it private, but I mean, that's not a standard feature. With synthetic data, if you don't do extra protection, it's also can be very highly susceptible to a privacy attack called membership inference attack that I will introduce more in a minute. Okay, that looks pretty bleak. Is there any hope? Fortunately, there is. And a lot of these positive solutions build on a framework called differential privacy, which is a mathematical framework. You can mathematically prove that an algorithm will preserve privacy. It's a property of the algorithm that's based on kind of like a thought experiment, that you have two data sets that differ by the contribution of a single individual, and then the differential privacy criterion requires that the probability of obtaining any outcome should be almost the same for both of these adjacent data sets. And then what this means is that it effectively gives everyone who contributed to the data set a plausible deniability. It would have been almost equally likely to get this exact same result, regardless of what my data was. Therefore, you can't learn much about my data. There's also, if you look at the equation here, there's this parameter epsilon that defines how close this has to be. And obviously, you can make it extremely private, which then means that you aren't able to learn much from the data, or you can make it very loose and then it becomes meaningless. So just saying something is differentially private doesn't mean much. You have to check, okay, how strong is the guarantee actually? How is this done in practice? There's a lot of work implementing most machine learning algorithms you can think of with differential privacy. The basic building blocks typically are that you need to somehow limit the impact any single individual can have in the result, and then you need to add a bit of noise. And the main workhorse for differential private learning is an algorithm called differential private stochastic gradient descent, which can be used to for something like fitting deep learning models, or basically any gradient-based optimization. Okay, that's very nice in theory. What's the catch? The catch is that it tends to have a very strong negative impact on your on the utility of your models. So this is kind of a standard image classification benchmark, CIFAR-10. In non-private setting, you can easily get over 95% accuracy with that. Now, if you kind of train a model from scratch with differential privacy, with a reasonably strong privacy protection, it's very hard to get above 60% accuracy. And that, of course, means that, I mean, your very good classifier becomes something that's completely useless. So that's a bit of a downer. Fortunately, during the past few years, there has been a lot of new hope in this area. So there has been a lot of work showing that if we kind of start with a pre-trained, kind of like foundation model trained on public data, then we can fine-tune that model on the sensitive data. And with these fine-tuned models, we have the blue line there. That's gets you very close to the non-private level. Of course, it depends on kind of how similar your pre-training and fine-tuning data are, and there's kind of lots of caveats that, I mean, is this, now we are kind of supposed to be doing something private, but we are using a lot of data that doesn't get these privacy guarantees. So there are kind of caveats to this, but I mean, for a practical application, I mean, you could, I think, I mean, this would be kind of you could take some generic foundation model, then fine-tune that with medical data, and actually get differential private models with a reasonably good accuracy. Okay, so with that background done, I will next go a little bit more deeper into how we actually analyze the privacy of models using specific privacy attacks and potential defenses against those attacks. Then towards the end, I will talk more about benchmarking. So how can you run a privacy challenge? What are the obstacles for that? And a bit of outlook and conclusion. Okay, so the first basic privacy attack that I already showed a bit, and this is by far the most commonly used one, is what's called a membership inference attack. And these attacks can be formulated as games. So this is a two-player game. We have a challenger here. And in the membership inference attack, the challenger randomly selects one of these two data sets. So either including this cat in the training data set or not, and then trains a model using this data set. And then the task of the adversary is to figure out whether this cat image was part of the training set or not. So membership inference is predicting whether the target point was a member of the training data set or not. It's a very good question to ask whether this is kind of like a realistic attack we should be worried about, because of course, I mean, in order to implement this attack, the adversary has to know the target point, so it has to know the data that they are attacking. But we'll see in a minute that this actually is relevant. And I mean, there are other more kind of more realistic attacks, and this is actually, but defending them is rather similar. How would you do this in practice? So basically, what the adversary needs to know is whether this particular image was part of the training set from the trained network. So basically, the adversary has to build a model. What does it look? How does the trained network look like when this target image was part of the training set, and how does the target model look when it wasn't? So a typical approach for running this is using so-called shadow models. So the adversary doesn't know the rest of the training set, but I mean, they can get some similar data, and then they can train models both with and without this target image. And then from these, they can then look at, okay, how does the trained network look like, whether this was part of it or not? So that's the basic idea of how this works. Okay, then for other attacks, now getting kind of into something that looks like a more serious privacy violation, attribute inference. Now the challenger just has one model to train, and the task of the adversary is to infer kind of a complete data point from the data set by having just a partial access to that. So the medical application might be that you know that someone was in some EHR data set. Maybe you don't know what diagnosis they had, but you have kind of like demographic information. So, okay, given that demographic information, how can you reconstruct the diagnosis? And the final attack that I will be considering is data reconstruction, which is even more straightforward. Now the question is just how do we get that particular piece of data without any information? And this is what the examples were with the Gen AI typically were about. So to summarize, there's quite a different set of assumptions for these. In the membership inference, it's just binary classification, was a data point part of the training set or not, with substantial side information on the training data distribution and the target point, going all the way down to data reconstruction, where you just given the model, get some data from that. One interesting point here is that, I mean, although these appear quite different, there's actually research that shows that the difficulty of defending against these attacks is more of a difference in degree than difference in level. So there's if you have to kind of choose from more possibilities in attribute inference rather than just a binary classification, it's kind of a more difficult attack and easier to defend against. But in principle, similar kind of techniques. If something works against one, it works against the other. It's just a question of how tight parameters you need to use, modulo whether kind of we are looking at kind of worst case vulnerability or average case vulnerability, which is another challenge here. Okay, so how do we? So that's kind of your basic attacks, and because these are somewhat kind of related, I will focus mostly on the membership inference. That is by far the most commonly used one. So how do we evaluate membership inference attacks? Essentially, a membership inference attack result is a binary classifier, and now we need to characterize how good that binary classifier is. And obviously, this information is contained in the ROC curve, which looks at the trade-off between false positive and false negatives. And in the case of membership inference attacks, usually the thing we worry most is being very confident about someone being a member. So we care about the true positive rate at a low false positive rate. And ideally, we would want that to be close to this random guessing level of the diagonal in the ROC curve. You may also notice that the ROC curve here is plotted on a log-log scale. So this is to emphasize the low FPR regime that is of most interest. You may notice that the plot here contains a couple of lines with the magic parameter S. The S here denotes how many examples in this particular data set we had of a particular class. And it turns out that this is a very common phenomenon, that as you increase the number of examples in per class, the attack becomes less vulnerable. So the yellow line here is there's very little advantage the attacker has over random guessing, whereas the brown one here is pretty susceptible. So this is actually kind of a common phenomenon that you have. I mean, as you have more data per class, things become more vulnerable. There's some recent work where we looked at this across a number of data sets, and it's kind of all looks surprisingly well fitting to a linear model. Is this enough to kind of practically that we just train these models without any protection, and then that will magically make us better? Unfortunately, it seems not. So when we extrapolate from this linear model, it turns out that in order to get kind of a reasonably strong protection for the most vulnerable ones, you would need of the order from tens of thousands to millions of examples for each class in your classification problem. And so good luck trying to find a million cases for some rare disease that you might be interested in. Further examples of kind of privacy techniques that are used but may not be as reliable as one might hope. So this is with synthetic data. There seems to be a very common measure to somehow measure the privacy by the distance to the closest nearest record in the actual data set. And there was some interesting recent work that showed that there's actually this distance to the closest record has almost no correlation with the vulnerability to the membership inference. And you can have extremely high vulnerability to membership inference, although this distance to the closest record seems like it's should be okay. So this is kind of illustration that it's not that easy to get things right, and you really have to be careful in how you measure this privacy. Another example of heuristic defenses is that, of course, you can just do something and then test, okay, let's mount an attack and see how that works. So here's an example. This is from a recent paper on unlearning, where they were evaluating, kind of looking at work that had proposed some unlearning approaches and then testing with a membership inference whether that actually works. And turns out that if you have a weak membership inference attack, it might be that your defense looks good, but then if you try with a stronger attack, then the attack accuracy increases, and it's no longer safe as you thought. Yet another technique that has been used to propose preserving privacy is training with synthetic data. So here's kind of some results from a recent paper from ICLR this year that looked at whether training with synthetic data, how good is it in actually protecting privacy. They were again testing it with membership inference attack, and interestingly, it turns out that it's training with synthetic data. Some of the techniques provide very little protection, and for the ones that actually do, you tend to get a lower accuracy than you would, or always get a lower accuracy than you would if you train with a standard differential private stochastic gradient descent. So it's kind of synthetic data from this, on the basis of these results, seems to be more like a pseudo protection that's not really as efficient as training with differential privacy. Okay, I've been talking a lot about differential privacy on the kind of how that gives you protection, but how does it actually link to these attacks? So this is, so if you look at membership inference attack and the success of it, you can think about that as a hypothesis test. You want to perform a hypothesis test, and you want to be able to detect the members. And it turns out that differential privacy can be interpreted as providing lower bounds for the false negative and false positive rates of any test that would perform membership inference. So graphically, it means that, we want, when we are kind of running our attack, we would want something that gives a low false positive rate, low false negative rate. So we would want to be here close to this corner. But with differential privacy, we are constrained to be in this shaded area here. So essentially, you are bounded away from this corner of zero error. There's a number of different definitions of differential privacy that differ a bit in how you parameterize this, but basically all of them can be somehow interpreted as giving this kind of protection. So to summarize the part of attacks, as nice as it would be to kind of be able to use some of these heuristic privacy metrics as a shortcut, unfortunately, they rarely seem useful. And there's a lot of these examples of how these fail. So really, in order to reliably measure privacy, we need something like a strong privacy attack that's ideally tailored for a particular algorithm, or then we can use differential privacy that is based on a mathematical proof for a particular algorithm. The difficulty with differential privacy is that it's a property of the algorithm. You have to prove it, so you can't verify that from the outcome. Differential privacy also has a nice property that it's a worst case bound for all attacks, for all target points, whereas attack evaluation is usually more statistical, that you have to be doing some averaging to get these ROC curves. So it might not be that easy to measure the privacy risk of the most vulnerable individuals. Another point that reflects, so in the challenge, we had these two different tracks. There was one for bulk RNA-seq, another one for single cell. So here we get to the question, okay, what is the privacy unit? In the single cell, we could do kind of like cell level privacy, which kind of would be more similar to what you would kind of, because in the bulk, you only have kind of like one profile per individual. But then that's, of course, a much weaker concept than kind of really doing individual level privacy. So this is another complication that needs to be taken into account, both in the attacks and in the DP. Okay. So now with the background of, we have the DP proofs, we have the attacks, how do we build benchmarks and challenges for privacy preserving algorithms? From this, I would say that, I mean, there's basically two types of competitions that we could run. The first one is a very simple, we just go for algorithms that have these, provide these formal guarantees. So you specify a level of differential privacy, and then the competition is about who gets the best accuracy with that, under those constraints. The other one, that's also what we employed in this challenge, is a more empirical competition where we have two competing teams. The blue teams develop privacy-preserving solutions, and then the red teams try to attack those. For the formal privacy competitions, this is very easy. You just define a task that optimizes the accuracy at a given level. Some of the challenges with this approach is that it limits the scope of solutions. You kind of are forced to this one formal model, and there's not much room for creativity. Some practical challenges are that, because I mean, how do you verify the DP proof, which you typically write on paper? How do you verify that the implementation actually matches that one? There's a lot of fine details with that. And finally, there's a problem that, I mean, privacy relies on true randomness. So you also need to be very careful about how to prevent the participants from cherry picking a random seed that just gives them very good performance. Okay, for the blue team, red team task, that's a bit more challenging to set up. First, for the blue teams, in order to make it a fair competition, you really need to somehow, because privacy utility, there's usually a trade-off. That, I mean, if you require strong privacy, your utility will go down. If you're not as careful about the privacy, then you will get higher utility. And then if you have two solutions, one of which is more private, one of which is less private, it's kind of hard to compare those. So you somehow have to pick a operating point on this curve. But because the privacy is measured by these attacks, then the easiest way is to kind of calibrate by utility. So saying that, yes, we want at most this much loss over the non-private solution. Then for the red team, the challenge here is that the optimal attacks are often have to be tailored for a particular submission. It's kind of often possible to create some small tweaks in your solution that would evade a known attack, but then might not provide true privacy. And then if you were successful in your organization, you had lots of these blue team submissions, how do the red team participants pick which one of these to attack? Because it's a lot of work, and membership influence attacks are also computationally rather expensive. So really, I mean, this is a nice setup in the sense that it can reflect kind of a real world risks, but the challenge is that, I mean, your privacy relies on having these red teams actually put a lot of effort into testing these solutions. And you will also need a lot of a longer competition time to be able to kind of give both of these teams that can't happen at the same time, give them both enough time. Okay. Towards conclusion, a couple of points that I wanted to mention. First one is that, I mean, if we kind of look future, I mean what's happening in the conference, it's all about these foundation models. You have foundation models for DNA, foundation models for XYZ, And we also saw that, in the privacy setting, this is, of course, good in the sense that, if you have a pre-trained foundation model trained on non-private data, it's easier to get a good privacy utility trade-off. However, this does create a challenge for benchmarking, which, of course, that's for any ML problem, there's a challenge that, if your training or testing data was part of the pre-training data, then you're kind of in trouble with that. But I would say that this is even worse in privacy, because we don't give any guarantees for the pre-training data. And if your supposedly private data was part of the pre-training data, then it's then it's a problem. And of course, when we are developing these challenges, well, in a real setting, of course, your whatever private health data you had probably wouldn't be out there in the internet. So the providers of the foundation models wouldn't have trained on that. But for running our challenges, we need data that people can access. So that's kind of a problem. There's a very nice paper by Florian Tremeur et al. From ISMB last year, where they discussed these in a lot more detail. Maybe also reflecting a bit on this question of anonymity. So we saw that the EHDS requires that the results, well, at least eventually requires that the results of this analysis of health data should be anonymous, which under the GDPR is defined that, this shouldn't be able to link a particular data to an identifiable individual. And this is specified as using means reasonably likely to be used. And this is, of course, a big loophole. Now we if we're thinking about now we have to think about the context on where these systems are being deployed. So if you are sharing your synthetic data set or a model for open science on the internet, the means someone would reasonably likely use to break that will be very different from when something is integrated into a hospital system and is being only used by doctors there through some very restricted interface. So which of these attacks are realistic in which setting? I think, that's a very interesting question, and there's a lot of work to understand this better. There's also the ongoing debate on whether the ML models are anonymous at all. This seems to be turning towards the opinion that many of these machine learning models trained on personal data are not anonymous, and then this is something that you would have to worry about. But this is not really fully settled yet, and there's some also interesting legal questions and discussions expected with that. So that's basically what I had to say. I guess being here, I really support the CAMDA ideology that these competitions and benchmarks are very important in promoting development of better algorithms for the real world. And as there is this clear need for privacy preserving algorithms, we do need these. Then how to do this in practice? There were these two basic approaches, either going with a formal privacy or then with this something that incentivizes the specific developing these tailored attacks against a specific algorithm. The difficulty here is that, as I know Hakim especially has noticed, that, these are not easy to run compared to standard ML competitions, where you just have your test set and then have everyone submit their predictions against that. This is a lot more work, but this is, I think, this is important. So finally, I'd like to thank my collaborators. So this organization of the competition has been supported by the European Lighthouse on Secure and Safe AI, ELSA project, and Hakim especially has been vital for running this. She will be presenting in a minute, but also my other collaborators here. And yeah, And thanks to all of you for listening.
Thank you. Any questions?
Hey, thanks for the talk. So is there a big difference between reconstructing a specific given sample or just any sample that has being used for training? Because it feels that in your examples you try to reconstruct a given sample.
Yeah, that's true. So there is, I didn't go into the fine detail, but obviously it is very different of whether you kind of want to reconstruct a specific sample or you just reconstructing any training data. So that's indeed the case. I guess, I mean, with and that's also kind of in the examples here. Where are we? So in the examples here, the kind of for the LLM, there's just this generic. You kind of somehow with this prompt, you get it into a state where it starts generating something from the training data. Whereas in the image generation example, you can get it to create a specific, reconstruct a specific one.
Hi, can you speak more about how you would think about generating evaluation data sets, given that we don't know what was included in pre-training for privacy data?
That is a great question. I guess what's typically kind of a privacy, kind of the safest solution for that is that we would limit our pre-training data to some known collection. So for instance, I mean, there's kind of one of the techniques proposed in this Trummer et al. Paper is that, let's say that, I mean, we consider in an image classification setting, we assume that, let's say that ImageNet is considered public information or some size of lion. Maybe in the HR case, it would be, okay, let's say that, I mean, some version of Mimic is public information, and then you don't test on that, but you can kind of pre-train on that. That would seem like kind of the easiest choice, but yeah, other than that, I guess, I mean, this is kind of fortunately, this is a common problem with the others as well. So.
Any other questions? I think it's I work at a hospital, so I think it's one of those fundamental problems these days. In computations, thank you for addressing this. But in your mind, is it hopeless to actually be able to generate a data set that it is secure but still useful?
Synthetic data generation is hard. And I guess this is, I mean, in some level kind of doing privacy preserving learning, I mean, this is something that, I mean, when I first saw these results, I mean, this was kind of very hopeful for me that, okay, you can do this. The challenge with synthetic data is that, I mean, now you're not trying to solve one classification problem, but you are trying to solve all possible problems you could solve with that data set. So this is a very difficult problem. I mean, there are, of course, works that do this, but I guess, I mean, there seems to be kind of this mismatch of expectations. And I mean, the medical cases where you most want it is something like a rare disease where you have a handful of patients, maybe some hundreds, and then you have this extremely kind of a lot of data for each individual. And the case where synthetic data is easiest if you have kind of lots of individuals and not that much data for any individual. So you're kind of like going to the opposite extreme on both dimensions, and that makes it very, very hard. So, but yeah, I guess, I mean, this is something, and I mean, also, I mean, for the actual attacks and what are the risks, I think, I mean, this is an area that there has been a lot of progress since, but I mean, this isn't as developed our understanding of what are really the privacy risks of synthetic data compared to what it is in these more typical like classification models.
Yeah, agreed. It's really a tough problem, and when it gets to, in old days when we're talking about whole genome sequencing data, for example, and that required, the intervention from the governments to actually, set up rules for, the implication of knowing somebody's sequence versus, their healthcare. So there, I'm sure there are a lot of discussions about the genetic data. I was wondering, maybe, the organizations and the government agencies that you mentioned probably have to sort of continue discussing how one might be able to address this, because it's certainly one of the most important issues.
Yeah, I think, I mean, genetic data is kind of another kind of its own kind of worms. I think, I mean, for this, something like kind of what these databases are doing, that, I mean, you can get access for research. How well you have to protect that is then a question. But I mean, I kind of full genomes being openly available on the internet, I mean, that's a pretty long way to go. And but I guess, I mean, that's what we're working towards, and let's see how far.
Yeah.
But let's see how far we can get.
Yep. Any other questions? If not, I'd like to thank the speaker.